Hello everyone, in today's video we are going to continue with the tutorial series and exploring more about the 7-segment displays and using logic and projects from the past to make something more exciting. For today we are going to make a 4-bit triple adder and converting the result to a binary coded decimal to display it as a 2-digit decimal number. Before we start with the tutorial, I'm going to explain some concepts that we are going to use. First, I will start with the full adder. I will put a diagram for the logic of the full adder on the screen and explain. We can see that full adder has 3 inputs, which is A and B and C and A and B, the inputs that we are going to add to each other, and carry in will be the same. We will add the carry in to A and B. But mostly in this tutorial we will use the carry in as 0, at least for the first adder. And then to make a 4-bit ripple adder, you have to connect, as this diagrams show, the first adder will be connected, its C out will be connected to the second full adder as a CN, and then you will have the inputs A1, B1, A2, B2, and so on. And we will have the outputs C S0, S1, S2, and S3, and the last thing C out. Mostly we're not going to use the C out as well in this tutorial because we are just going to work on the 4 bits, which is the summation result. Because what we going to do is this: we will have a 4-bit number, okay, and we will display this number as 2 digits in decimal. And to convert that, the easy way, we should make that number as a binary coded decimal. So let's talk about the comparator first. If the number is higher than 9, our second display must show 1. If it is not, it must show 0. And depending on that, we will choose which our input we are going to take, the main switches or the input that's coming from the circuit A. Well, circuit A is going to do that job. It will take the number and add 6 to it. So we will result as the 4 bits will be the first 4 bits of the binary coded decimal. For example, if we had 4 ones, the circuit A, the A result will be 5 after adding 6 to it. These are decoders that we have designed in the previous tutorial. And the last thing, we will see the 2-digit number on the screen, as we will see in the last part of the video as the usual. Alright, so this is the main module for our tutorial today. We are going to use, as I said, 4 switches, and these will be defined only just to turn them off, so we don't have that state that the red LED be between on and off. And the last things will be a 2 7-segment displays for displaying a 2-digit decimal number. Well, from the diagram I have explained a while ago, I will start making now the modules. I'll just do them in a separate files. The first one will be the comparator. For this module, the comparator, we will compare and check if that input is bigger than 9, If it is bigger than 9, we said the z will be equal to 1. And if not, it will be equal to 0, which means we have a number higher than 9 or lower or equal 9. So for the comparator, our input will be the switch, which I'll just name it here input. It will be input in, and it is 4 bits. And we will have a 1-bit output register. I will just name it S. Okay. I'll say I will use an always statement and a star between the brackets because of combinational logic, and check for the n if it is bigger than 9. Our s will be equal to 1, else s will be equal to 0. So this is for the comparator. Now let's go to the next part. Okay, now we are going to move to design the circuit A. But before that, the circuit A function, as I have explained before, we are going to add 6 to the input that we have, so we can make the number from to be in binary to be transformed into a binary coded decimal. So we need an adder. We need actually 4 adders to make a 4-bit triple adder. So to make that work, now let's design the full adder. Okay, and then go back to circuit A. For the inputs and the outputs, we're gonna have, as it shows in the screen, the diagram, we're gonna have the input Cn, input A, and input B, and output S, and the last thing, output C out or the carry out. And we need a wire for the XOR result, that it is between the A and the B. So I will just name it XOR R for XOR result. I will assign that value to be A XOR B, and I will assign the S value, which means the sum value, to be XOR R XORed with the Cn. And the last thing, I will call the mux. It's a 2 to 1 mux, not like the one we have made in the first tutorial. It was a 4 to 1 mux and it was 2 bits. And this one will be 4-bit and a 2 input mux. So I can just show you the code for it. I'm not going to go through step by step because it's just a little different than the other mux, not that much. It will be easy to understand it. So the selection value will be the XOR result, and the X value will be B, and the Y value will be Cn, and the output from that mux will be the carry out. And like that, we have designed a full ladder. And here we have the summation value, summation output result. And here we have the carry out result. And now let's move to the next step. And now back to the circuit A. we have a 4-bit input and the output is 4-bit as well. So to imagine that the binary coded decimal actually is made for the 2-digit is made from 8 bits, but here in the circuit A we will output only the first 4 bits. So like that we will have the ones, and the tens will come from the comparator. If the comparator result was 1, we will have 1 as tens, and if it was 0, it will be just 0. Okay, I will use wires as well. I will name them. I will name the wires C1, C2, and C3. These are for the carryout, so we can connect four full adders to make a 4-bit ripple adder. Full adder, and this is adder 1. The Cn will be 0, and it will take the first bit from the input, and it will be added to a 0, or a 0 will be added to the first bit of our number. A 0, here it's A, and the output or the sum output will be the first bit of A, and the carryout will be C1. So this carryout will be the next adder carry in. Okay, so we can just copy the circuit 4 times, and let's just name them like 1, 2, 4, and change the bits here. And instead of giving it 0 as a carry in, we give it C1. And instead of giving it added to a 0, we will add a 1 to the second bit, and here a 1 as well. So as we know, to present the number 6 in the binary system, it will be represented like that. So you can see here the pattern we have for each bit: 0, 1, 1, 0. That's a number, the number 6. Here the carry out will be the C2, here the C3, and the last adder, the carry out is not needed. Here we connect C2, and here C3. Third bit on the input and the output, and the fourth bit on the input and the output. So like that, we have made the circuit A from using 4-bit triple adder, which is made from 4 full adders. Okay, now we are going back to the main design that will connect all the circuits together. I will start assigning all the red LEDs with 0, so all of them will be turned off. And I will need wire B, which is 1 bit. It's going to be for the output of the comparator, and I need 4-bit wires, A and R. A will be the output that comes out from the circuit A, and R will be the output that comes from the multiplexer. And now let's use the module, the comparator module. I'll name it comp. I will give it the input, the switch input, and the output will be B. And I will do the circuit A now, like this. And I will give it the input, the switch input, and the output, the wire output A. And the 4-bit multiplexer, 4-bit width multiplexer, which is 2 to 1 multiplexer. I'll name it max1. It will be like this: the input, the switch input, and the A input, and the selection line, which is B, that comes out from the comparator, and the result, and the final result that comes from that multiplexer. And the segment decoder, I'll name this one tens decoder, and the other one will be named ones decoder. And I forgot to mention that the decoder we have already made in the previous tutorial, so I'm not going to do it from the beginning. I'm just going to use it. If you want to know how to make that, you can go to the previous video and check it out. I will show a code snippet of it if you want as well. And now this multiplexer will take the B result from the comparator to say if that number has 1 or 0 in the tens digit, and the output will be showing on the second 7-segment display. And this one will take the result from the multiplexer, which is the ones, and the result will be on the first 7-segment display. Like that, we have our code ready, and now we should just compile it and test that on the FPGA. I will skip the part of the pin assignment. It's so easy, and actually you can use something like a system builder. Each board, or I won't say each board, but most of the boards from Altera has a system builder for each one. For example, I use the DE-10 standard system builder, so it will assign the pins for you, so you can save time from doing that boring thing. Okay, here is the Quartus Prime window. We have opened the project, but before compiling, make sure that you have all the right files, because we have written the code of each module in a separate file, and not in the one file, so the Quartus Prime can read those modules and it won't cause a compilation error because of that. Now let's compile the whole design. Alright, here we have got a compilation error for something. Actually it is so stupid, which is says cannot connect instances port both by order by name. Make sure here we are using one method, by order or by name, and here I just forgot to write a dot before each name of the variables here, and I think this should solve our problem. I will compile the design again. Okay, we have compiled the design successfully, And now we are going to program the FPGA. We just go to programmer and program the FPGA. And now we will see the work on the FPGA and test each number from 0 to 50. Okay, now we have our FPGA on. Let's try and test out the output that we will have. Uh, as I have said, the first four switches are going to be the input. So we can check. Here it reads 1, and then 2, 3. Now we have 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 13, 12, and so on, up to 15. So this is the design and it's working on the FPGA.